All right, if you like, we can start again. We had this before the break. We were developing Langevin's approach for stochastic trajectories of Brownian particles. The way I set it up, this is actually nonsense here, is that this is the noise correlation. So the noise has mean and mean zero and the variance given by Kronecker deltas and correlations that are short-ranged in time. I didn't assume that it's Gaussian, but let's assume that on top of that distribution is actually Gaussian, because I'll need this later. And then you can show, and we do this step by step, maybe today I'll show you that this is equivalent to a Fokker-Planck equation, so an ensemble picture. And on Wednesday next week, I'm going to show you that this is also equivalent to a path integral description of the Brownian particle. And both are nice and both are important. But let me start with the Fokker-Planck equation. From that, you know, Fokker-Planck equation can be derived if you know the moments, right? And that's what we do now. We calculate the moments, and for that, let's write the Langevin equation in a form which is a difference form. So I consider the velocity at some t plus delta t and subtract from it the velocity at time t, and imagine that this delta t is a small time scale. And then the first term is very simple. It's just as if you were doing forward stepping in solving the differential equation, right? So you have, with a very basic scheme, by multiplying the velocity at time t with delta t, and that gives you the velocity at some time later. And there's also an increment, and this is actually a very special increment, as we will learn, that mimics or that emulates what the particle collisions do, our Brownian noise. And I call this delta w of t comma delta t, and it's defined by the integral of our Gaussian white noise over this small time interval between t and delta t, eta of tau, and we call this a noise increment. All right, and we want to infer, so that's the goal, is to infer the probability distribution, or the equation for the probability distribution of delta v from the PD of delta W. Right? Now delta W, as you see, this noise increment, is a sum of random variables. It's an integral over the Gaussian white noise over this time interval. Eta is Gaussian distributed. Any sum of Gaussian distributed random variables is also Gaussian distributed. So we know this must be Gaussian distributed. And then it suffices to actually calculate the mean and the variance in order to know what distribution function of delta W is. The mean is 0. That's trivial, so we only need to look at the second moment. So let's do that. Delta W of k, delta W j is this double integral where in both cases I integrate over this time interval between t and t plus delta t. D tau and d tau prime. And then I have the average eta k of tau, eta j of tau prime average. That's what I need to do. Well, the etas are Gaussian, they are short-range correlated. Yeah, I know the expression here. It's the noise amplitude Kronecker delta and the delta function in time. So this is very simple. This integral just becomes a constant. So Tm theta times kbt times delta kj times delta t. And here you should already notice that this is an interesting object. The first term here scales like what? It scales like delta t. The second term scales like delta w. But delta w squared is typically delta t. And that means this second term scales like the square root of delta t. This will become important when we discuss stochastic differential equations, because this is very unnatural if you think of an Euler scheme or any other scheme of evaluating a ODE. There you won't never have something like square root of delta t. But you have here, because of the nature of the Gaussian noise being related to a random walk, and these random walks have this property that the variance scales with delta t. All right, since we have that, we know what the distribution function is, right? We know the second moment, so I can just write down the distribution function for my delta w. But this is also the distribution function of delta v, right? Because delta v is related to that by this simple transformation. So this implies that the distribution of the function for the conditional probability of having a velocity v at time t and some velocity v prime at some time delta t later times the volume element of the velocity d3v prime. This is given by a Gaussian distribution with that moment. So here in front we have a normalization factor, and I define the sigma in a second. And we do have here the exponent of minus delta w squared over 2 sigma squared d3 over the volume element of delta w, with the sigma being the variance, the amplitude of the variance. So sigma squared is this prefactor that we have here on top, so 2m times theta times kbt. Okay? So that's very straightforward. You have a Gaussian distribution that you feed in, and you get, for small time increments, also a Gaussian distribution for the conditional probability. Well, now we do have the central object that we need in order to create to calculate the moments for small time increments. Remember, when we constructed the Fokker-Planck equation, we used that here in order to calculate the drift vector and the diffusion matrix. So AI, the drift vector, is the average of the increment divided by delta t, And the average over the increment is taken with respect to this conditional probability. So it's an integral over this distribution function, delta vi p at time t plus delta t, given what it was at time t. Okay. And that here, then when I calculate this, this gives 1 over delta t. Here the first term is the drift vector, vi delta t, and the second term is delta wi over m, averaged over delta w distribution. Right? So I just inserted here the delta vi, which by our construction here is the drift term plus the noise increment that you have here. This is this. Right? And what we have to then take the average over is the average over the Gaussian increment, because that's the feeding noise in our system. Well, we know that delta W is 0, so this is minus theta Vi. And note here, this V here is not a stochastic variable. It's the condition. So I start from a velocity V at time t, and I ask what is the velocity at time t plus delta t. The random variable is delta V, V minus V prime. The condition is on V. So maybe I should say that this is an average conditioned on V at time t. Okay, and that's why there is no real average here. This is just a 1. Yeah.
What's the line above the delta Vi in the prime, right?
Well, I called it delta Vi.
Ah, okay.
So delta Vi is Vi prime.
No, it's fine.
So just to be clear, by definition. Okay, so we have it. The drift is the deterministic part that we feed into the Langevin equation. No surprise, because if you would get something else, you should be alarmed, and the whole approach would not really make sense if you get the other drift than the one you put in. So Bij is a similar type of calculation. So you do the average of your covariance at different Cartesian indices I and j. Let us spell this out again. This is the integral over the random variable, which is the velocity at time t plus delta t, so V prime. And then I have the differences of the velocities, and I want to average over this conditional probability for the velocities. I do the same as before. I just insert the expression for our velocities. So that's the average, again in the same sense. It's an average over the Gaussian distribution of the noise increments, conditioned on having a fixed velocity v at time t. So this is then, just copy this, minus theta vi times delta t plus delta wi, so the noise increment at coordinate I. Here the same with Vj, delta t plus delta Wj over the mass averaged over delta W, conditioned on having a fixed velocity at time t. Well, what's that? Okay, here, this term is delta t times delta t. It's delta t squared. In the limit delta t going to 0, maybe I should put this here, limit delta t going to 0, here the same thing. This vanishes. The same is true if you multiply the deterministic part with the random part, because that, well, for two reasons. Delta W is 0. That's the reason, actually. But also from a time scale reason, delta W scales like square root of t, so it would already be higher order, even if the average would not be 0. The only term surviving is delta Wi, delta Wj, because that correlation function, as we showed, grows linear in time. And then it cancels off with the delta t that you have here in front. So that is then given by 2 times kBt times theta over m, because I have 2 m's here in the denominator, times delta ij. Right, so you're done. You have the first moment, and you have the matrix of the second moment, and since we're assuming Gaussianity, that's all we need. We can immediately write down the Fokker-Planck equation now. So what is it? So this is from our earlier analysis, the Fokker-Planck equation for the conditional probability must be of the form that given some condition at time t naught, so you can specify this if you like. You can say at time 0 you have some velocity v naught. This is dv. Okay, so it's a derivative, a gradient in the velocity. The drift vector is theta v. And here we again have the conditional probability. And then the second term is kBt times theta over m, because remember the coefficient in the Fokker-Planck equation is a half of the diffusion matrix, and it's diagonal, and therefore I do have here the Laplacian in velocity space of Vt conditioned on some initial value. That's the Fokker-Planck equation. Now coming back to the earlier question, what does it converge to? What's the limit t going infinity? At t going infinity, you have this here in the form of a continuity equation. dTp is the gradient of a probability current. The probability current has to be 0. So probability current equal to 0. And then you have the first derivative of p is proportional to v. And that gives the Gaussian distribution, or the famous Maxwell-Boltzmann distribution. From that you get p v of t going to infinity conditioned on something. It converges to a Maxwell distribution e to the minus a half mv squared over thermal energy scale. And if you normalize it, this is the prefactor that you get. Right, so it's all nice and very, very consistent. So, yeah, please go.
You said, like, we assume that the W or the V is Gaussian, right?
Yeah. No, the W.
Yes, sorry, the W.
Yeah.
Exactly. And then, like, any higher jump moments would be 0 because of that, right?
The real reason is the reason you state. So all the higher moments are there. The jump moments are the moments that you get. But when you do the analysis, you will find that the higher moments are higher order in delta t. And as you then divide by delta t to calculate the jump moments, they are 0 because of the scaling of the higher moments. That's the correct answer. Yeah. Thanks for clarifying that. It's important. Okay, now we have seen this, how you map between a Langevin description and a Fokker-Planck description. And that's true in general, as we'll see later. But let's now look at a different level of analysis for the Langevin equation. And that goes under the name of overdamped Langevin equation. The systems we are interested in, and that's kind of mostly where this is applied, is overdamped systems, meaning inertia is subleading in these systems. So you only have friction and force balance that determines the equation of motion. Okay. Then, question would be, if you start out from an equation for the position, which contains all the terms that we worry about, namely inertia, damping, and forces from a potential. Potential here is U. And our Langevin noise, eta. How would you argue that you can neglect that term? So I will just do it here. And in my lecture notes, I'll give you the calculations of how this is done. It's a bit technical, that's why I don't want to do it on a board. But basically, you can see that on the relevant time scale, where all momenta are relaxed, you can get away with description that's fine if you just look at terms that don't contain inertia. So the friction term, the damping term, and the forces that you have. Okay, so you reduce to force balance in the overdamped regime. Well, then you have, in this overdamped regime, a different form which we want to write such that on the left-hand side I have the time derivative of the position, and then we have minus mu gradient of u plus psi, and where I have defined mu as 1 over m theta. So it's the inverse of our damping, our friction coefficient, and that's why this is called a mobility. And the noise also has to be rescaled because I'm dividing through the whole equation by m theta. So in that formulation, psi I is still 0, and the covariance of the noise at different times is 2 times mu times kBt delta ij delta t minus t prime. And this form of the Langevin equation that only considers the position variable is called the overdamped Langevin equation. Now, we can rewrite this a bit, and I hope I still have it on the board. I guess I don't, so you have to look in your notes. In your notes, we had the Stokes-Einstein relation that was relating the diffusion coefficient with the friction coefficient, and basically it was kBt over m theta. So, or mu times kBt. So recall that our diffusion coefficient is kBt over friction coefficient, which in our terminology with the mobility is now mobility times kBt. And then when you write it this way, the Langevin equation has the form dx dt equals minus mu force, so the gradient of u, plus square root of 2d times the unit variance noise lambda. And now you have a very clear form where the first term is deterministic drift because of damping, and a force acting on our particle, and the second term is diffusion, and it just represents the Gaussian noise from the thermal fluctuation, but it appears here in a very natural way that Brownian particles have to show diffusion, so the noise scale here naturally is the diffusion coefficient that you have. All right, now we had an equation that describes the motion of a particle in a force field. Remember the Ornstein-Uhlenbeck process, which was a particle in a harmonic potential. And there we derived the Fokker-Planck equation based on physical arguments on the first and the second moment. Now we can repeat these kind of calculations based on our Langevin approach, which is maybe a bit more systematic than the one we had earlier, where I basically said I guess that the noise term is diffusion. So let's derive in the same way as we have derived the Fokker-Planck equation for the velocity. Let's derive the Fokker-Planck equation for the overdamped Langevin equation. And this Fokker-Planck equation has a different name because it was invented not by Fokker and Planck, but earlier by Smoluchowsky, and therefore this equation is actually called a Smoluchowsky equation for the probability density of the position of our particle. So again, the same reasoning. We define the increments of our Brownian particles as being the position at some time t plus delta t minus the position at some earlier time delta t. And then we do calculate the moments. So what is delta xi average? Well, this is going to be, what is the first moment? The first moment is the limit of delta t going to 0, 1 over delta t of delta xi. Well, this is pretty straightforward. You'll see that if you look at the equation and you write it out, then you get a term that contains the forces acting on our particle and the linear term with the Gaussian noise. The linear term with the Gaussian noise has to vanish because the average of a Gaussian noise is 0. So all you're left with is the forces, and I'm writing this now as m times Fi, where Fi is minus diu. As usual, force is the negative gradient of the potential that you have. What is Bij? It's, as usual, the limit of delta t going to 0, 1 over delta t, and the covariance now of the increments in the position of my particle in the eighth and jth component. So let me write this out again. This is the limit of delta t going to 0. Then by the same argument as before, when I write the equation of motion in terms of the increments, the deterministic terms are of higher order, delta t squared. The terms that are mixed are 0 because the noise average is 0. And the only term remaining then is the one where I do have the integral over the correlation function of the noise. Lambda I of t, lambda j of t prime. Right, this is a Kronecker delta, so the whole thing is just 2d delta ij. That means, again, by the same argument as before, the higher order moments scale higher order in delta t, so they are 0 in the limit of delta t going to 0. And the corresponding Fokker-Planck equation, or better to say Smoluchowsky equation, for the position of my particle given the position at time 0. This is minus the gradient of the mobility times the force at position x, p of x and t on the condition, and then I simply have d nabla squared p of x and t conditioned on the initial value. But this generalizes now what we had in terms of the Ornstein-Uhlenbeck process. There I showed it only for the harmonic potential. This is true in general. You can always write that as a drift term that comes from deterministic forces acting on your Brownian particle, and the diffusion term is the diffusion term. It's proportional to the diffusion constant. Again, as t goes to infinity, what happens? This must approach the Boltzmann distribution, and for that it's again key that d and mu are related by the Stokes-Einstein relation. Okay, this is important. If that would not be the case, you would not get the equilibrium distribution being the Boltzmann-Gibbs distribution with a potential u of x. All right. So that's basically it for today. As said, the diffusion in phase space, I'll leave you for self-study. And next time, we're going to talk about the path integral formulation. That's going to be the next week. But let me recap so you see what we have learned. So we started from the Langevin equation being a drift term and a noise term, assuming that the noise is Gaussian distributed and only has and is characterized by the first moment 0 and the second moment being a Kronecker delta in the indices and a Dirac delta in the time with an amplitude to gamma that's related by the fluctuation dissipation theorem. You can map this onto a Fokker-Planck equation by looking at the increments and the moments of the increments. The first moment gives you the drift. The second moment gives you the diffusion matrix, and the higher moments, they are 0 because they scale higher order in delta t. And that then finally tells you a Langevin equation is equivalent to a Fokker-Planck equation, which is this one here. And that equivalence between a Langevin equation and a Fokker-Planck equation is always true. You always get it if you have something that is having a Gaussian distributed noise term. Then you can, for any equation that you write down, going through the same kind of arguments, always show there's a one-to-one relation between a Langevin equation and a Fokker-Planck equation. It's not true, and we'll see this later, that if you have a random process which has a continuous state space, that you can find a Fokker-Planck description, or you can find a Langevin description. That's not always possible, because in the end, this only has the first and second moment being relevant for dynamics, and there are quite a few processes where higher order moments actually do matter. What then still works is a path integral approach, as I will show you. Those path integral approaches are more general. You can formulate them for Langevin equation and Fokker-Planck equations. And later in the lecture, we will see you can formulate a path integral formulation for any kind of discrete or continuous stochastic process, and always have a valid formulation of the stochastic dynamics, even if a Langevin description or a Fokker-Planck description doesn't matter. So the second point was that for what matters in the field of soft matter physics and biophysics and much of what I know about these kind of systems, unless they're quantum, the equations you can usually get away with is that you go to the overdamped limit, where you completely ignore any kind of inertial effects, because they are relaxing super fast. It doesn't matter that you have inertia. And then all you have to worry about are equations of that type, where the velocity is given by a force times a mobility plus some random force, and the random force contains the diffusion coefficient as the noise amplitude. You can generalize that to many particles. You just write here an index for a particle, and you rewrite this as a pairwise potential between many particles, and this here then a noise term for each individual Brownian particle, and then you immediately arrive at an interacting many-body system which is stochastic, and then you can ask questions like, what is the equation of motion for a many-body system when I coarse grain from a particle coordinate to fields like the density field or the velocity field? And we'll do this later in the lectures. Thank you for your attention.